All right, hello everybody. So we're really going to dive into things today. We've been talking about electric fields a little bit, and we know that an electric field is going to cause a charge to feel an electric force. And what we're going to talk about today is how do we create an electric field? And I don't think this will be incredibly surprising to everybody, but it turns out that you can create electric fields with other charges. So we know that this charge might feel an electric field, but we can make it by having some other charge over here. And we're going to kind of think about the most straightforward case today, which is imagining that I just have a single point charge. Maybe I'll put it right here. And I want to figure out what is the electric field due to this point charge kind of everywhere else in space. We know the electric field can be different at different places in space. So that's kind of our task today. And we have a rule that we can use to do this. In fact, you investigated this very rule in your lab, and it is called Coulomb's law. And I'm going to write Coulomb's law up here. You can see that it's got a nice kind of equation up there. But we're going to try to interpret and understand this equation kind of graphically here. So what I'm going to do is I'm going to pick a location in space. And I'm going to mark it in blue over here. And I'm going to imagine that we're trying to find the electric field due to the red point charge in the bottom corner at the location of the little blue circle that I've marked there. So I want to think about what this is telling me. So the electric field, number one, is a vector. So I want to know what direction it points. And you'll see that there is a unit vector sitting here on the right-hand side of the Coulomb's law equation, which is r hat. And you may have seen r hat before. In fact, much of this equation might look really familiar from universal gravitation, but I want to go through it again because it's a complicated expression. And that r hat vector is the vector that points from the location of the source charge, which is the red dot here, to the position of the field point, the place where we're finding the electric field. So if I were to draw that direction here, it would point that way, right? Away from the red point towards the blue point. If I'd chosen a blue point that was somewhere else, maybe down here, I'd get an electric field that points in a different direction. This would be more like that. So that's the direction of the electric field. I also want to know how big this electric field is. And you'll see that that depends on a few different things. One of those things is how big is the source charge, right? If I have a thing with more charge on it, I'm going to get a bigger electric field. That kind of makes some physical sense. On the other hand, this R down in the denominator tells me how far away I'm standing from that charge. So that's telling me that the farther away I get, the weaker this electric field gets. I can, if I want, actually write this down. This R distance points from the red charge to the point where I'm finding the electric field. Right? I could label that little thing R. And that R is going to be different at every point in space. So this other blue point that I've drawn down here looks like it's about the same distance away. So I'm going to get about the same electric field. If, on the other hand, I were to go out here instead, I would now have an electric field that still points away from the red point charge, but that is going to be much smaller than the electric field at the earlier points that I drew. The last thing that you'll see in this equation is that there is a constant, which we'll call little k, and that's a fundamental universal constant that characterizes the strength of the electric force. The numerical value of this constant is over here. It's 9 times 10 to the 9, and it's got some units that make things work out nicely. So that's how we find the electric field due to a single point. At that point, we can use all the machinery that we've already developed to figure out how big the electric force on a different point charge is due to the electric field created by this one. And I'll show you a little bit of what that looks like here. We basically just have to multiply this electric field by a source, or sorry, by a test charge. And you'll see that I was very careful to label these two Q's differently, right? There is one Q that creates the electric field. That's Q source. and there's a different Q that feels the force from that electric field. That's Q test. And they both show up here in the expression for the force between 2-point charges, which is also known as Coulomb's law. One thing to be really careful about with Coulomb's law is to note that it's only valid for point charges, or as we'll see in a week or two, for spherically symmetric charge distribution. So I can take some charge and kind of spread it out uniformly on this sphere, and that works for all intents and purposes, just like a point charge does. All right, there's a practice problem over on Top Hat for you to take a look at. And if you have questions about it, you can come back and watch the other video.